here's a strong acid. We see the acid molecule. Hopefully you're able to see from where you're sitting. The acid molecule has a red dot and a white dot. Can you see the white dot from where you're sitting? Okay, so here's the pure acid as it comes into the water. All of the acid have their hydrogen attached. And as soon as it hits the water, if it's a strong acid, every single molecule releases a hydrogen. You can see there are no molecules in that strong acid solution that have their hydrogen still on the red one. They all have broken apart. As opposed to a weak acid, where here comes the acid molecules, they all have their hydrogen on. And when you look in the solution, most of the molecules still have their hydrogen attached in the weak acid solution. Only a few molecules have released hydrogen. Can you see it? It's a big difference between strong acids and weak acids. I would even tell you, it does go so far as to saying most of the molecules in a weak acid hang on to their hydrogen. Only a few of them give off. So the majority, and this is important to understand, the majority of the molecules are still hanging on to hydrogen. So strong acids are much better at giving off a lot of hydrogen. You get a flood of hydrogen when you dissolve a strong acid. You get a little bit of hydrogen when you dissolve a weak. Some are stronger than others, but in general, weak acids, the molecule pretty much stays intact. Okay, now where does this become important? Just a couple of examples. Yesterday, Emily?
So in a manner of speaking, the hydrogen is the proton?
Yes.
Okay, that's confusing.
Where did I say something about a proton? Or was that in the picture?
So it's in the book, and also in the book it's an acid, it's like
Yeah.
protons and
I didn't even catch that when I was looking at the picture. And I'm not thinking about it because I'm used to it, but you're not. Yeah, think of what a hydrogen is. The element hydrogen. It's a proton with an electron around it. It's that simple. So when you have a hydrogen ion, it has lost its electron. What are you left with? Just the proton. So yeah, and you're going to see later on in this, there's going to be the term monoprotic and diprotic. A monoprotic acid is an acid that has just one hydrogen, like HCl is monoprotic. It's got one hydrogen. Diprotic would be an acid with two hydrogens, like H2SO4. And that prot in the middle of those, it means the proton. So yeah, hydrogen ion and proton are the same thing. It's kind of weird, you know, we think about atomic structure and all that, and just one proton. What does one proton do? Well, that's a hydrogen ion. And that has tremendous impact on things in chemistry, the presence or absence of a hydrogen ion. After the reading quiz yesterday, I went over how to write the net ionic equation for a strong acid with a strong base reaction. You remember what the net ionic equation always looks like?
Yes.
Yep. I hope so. Even if you got it wrong on your reading quiz, now you won't get it wrong again, yes? So, I see a strong acid, and I see a strong base. Do you?
Yes.
Yep. When you're writing that ionic equation, if you have an ion, include the ion. Don't ever forget the ions if they're broken off of something. Like definitely, we've got a hydrogen ion, nitrate ion. Include the charges. What do you see in the next example? High and rubidium hydroxide. What do you know about high? Strong acid, rubidium hydroxide. Strong base. Same thing. Okay, that was easy enough. Yeah. H2C2O4. What's the name of that? What is it? That's not acetic acid. Yes. C2O4 is the oxalate ion. Oxalate. So this is oxalic acid. Oxalic acid. What?
Crazy.
All right. I'm laughing at you laughing. I'm not laughing at what you said.
It's funny because salads are vegetarian oxys.
Oh, an ox salad. Yeah, I guess that is. All right. So maybe it was funny. This is strong or weak. You know there are 6 strong acids, yes? Did you memorize the 6 strong acids? Yes, by tomorrow have them memorized. I mean it. There's 6 of them. I mean, come on. 6. on our half day. It would be beneficial for you to learn this. Jeez. Does anything motivate you?
No.
Say the word beneficial.
Okay, all right, now I'm talking your language. Good. Oxalic acid is not one of the strong acids. What are the strong acids? I thought we went through all this. We did too. I asked everybody. In fact, we went person by person. We remember doing that? The strong acids.
When did we do that?
We did it.
No, Mr. Moore.
I don't know.
Half the class wasn't here.
You still have to know it.
How are we supposed to know that we know something when we didn't even knowingly?
Here.
Okay,
Yeah.
so I'll say it again just because I'm trying to be patient. Know the strong acids. There are 6, and that's not one of them. But if you have any acid, any formula of a compound that starts with hydrogen, if you know the 6 strong acids, and your acid you're looking at is not one of those 6, then it's a weak acid. That's how we know the difference between strongs and weaks. You memorize the 6, and then all the others are weak. What do you know about barium hydroxide? Is that strong or weak? That's a strong base as well. Maybe you want to write this down. The strong bases are all the group 1 hydroxides. All group 1 hydroxides. You know how they're always soluble? So they'll be strong bases when they're with hydroxide. And, I don't know why I'm telling you this out loud, and I can just show you this, I guess. Oh, I had it covered up. All the strong acid, the group 1 hydroxides, plus the larger group 2 hydroxides. When I say larger, calcium, strontium, barium, the bigger group 2 hydroxides. Calcium, strontium, barium hydroxide. Plus all the group 1 hydroxides, those are all the strong bases. I didn't include the biggest of the alkali or the alkaline earth, francium and radium. Those are very radioactive elements. We don't ever use them for any chemistry, really. Those are used in nuclear experiments and things. I guess, yeah. Francium and radium on the bottom of those families, Fr and Ra, these 2.
Oh, yeah,
All right, we good with that? There's your 6 strong acids. Okay, so now when we get to this, we want to write the net ionic equation for this. This is not a strong acid, strong base reaction. So what do? I have a comment down here in red. Weak acids should not get broken apart when you write the net ionic equation. Remember when I was showing you the picture? I said the majority of the molecules hang on to their hydrogen. So that means when you have a weak acid, almost all of that acid is still 2 H's on the oxalate ion. Because of that, we don't write that separated. We write that acid formula. Even though the job of an acid is to release hydrogen, this is not doing its job very well. It's hanging on to it. So this thing is going to be written just like you see it. However, this is a strong base, so we're going to have barium ions and hydroxide. Anytime there's an acid with a base, there will be a reaction. The hydroxide ion is really good at persuading the hydrogen to leave. And when hydroxide and hydrogen get together, what do you get? You always get water. Right. Now, don't be falling into the trap of saying, oh, there's 2 hydrogens, so it's going to make H2OH. No. Hydroxide can only take 1 hydrogen. So we're going to need 2 of those hydroxides. Well, what do you know? We already have 2 of the hydroxides right there. But it's going to make 2 waters. And what's the other product? Remember, acid plus base yields what plus what?
Salt water.
Salt plus water. What's our salt in this problem? Right, the barium with the oxalate ion, BaC2O4. Not 2, sorry. Okay, the net ionic equation. Now, I shouldn't have done this, I guess, because we don't have anything in our solubility rules about oxalate. Are oxalates soluble or insoluble? Let's just, for the sake of having an equation right, let's say this is a soluble compound, therefore this is aqueous. what would be the net ionic equation for this reaction? Yeah, are there any spectator ions? Yes. That was a hint.
Yeah.
What is the spectator ion? Not the C2O4. Not the water. The barium ion is. The barium ion is a spectator ion. Here's why. Because it was broken off of the hydroxide. It's a strong base. So those came in separated. This is an aqueous compound. So those two are separated. The barium ion was free at the beginning. It's free at the end. So that's a spectator. It's not changing at all. The oxalate ion did change. Because at the beginning, because it was in a weak acid, it was attached to the hydrogen. At the end, it's unattached to anything. It changed. So it belongs in the net ionic equation. This is going to be a case, and we didn't see this with the precipitation. This is a case where only one of the ions is going to be removed as a spectator. And that's fine. You're going to have charges in your net ionic equation on both sides, and it's going to be fine. So this has to be written together because it's a weak acid. The barium ion, I'm just going to say that's gone. So the net ionic equation looks like this. H2C2O4 plus hydroxide ion, I'll balance later, yields 2, now I'm starting to balance. That's our net ionic. I do have to come back and put a 2 there. That's it. No barium ion. It's good for you to see this because when we do the lab, starting tomorrow, we're going to have a neutralization reaction, which is nice. Remember, neutralization, those are nice. No limiting reagent. Or they both, no excess reagent. You got a question?
Yeah. So if you write the complete ionic equation, it would be H2C2O4 plus Ba2 plus OH.
Yes.
Okay.
Yes. Still, that would be together.
Okay, so
Written
if
together.
it's a weak acid or a weak base, and it's like in the beginning it's together, and at the end,
Yeah, if it was
it's
reaction, it'll
together.
be
Okay.
rearranged. Yeah.
Okay.
Yep. Yeah.
So if you have a strong acid and a weak base, would that be the same result?
Yes. We're not going to see any weak bases right now. We're only going to deal with weak and strong acids. All the bases we're going to have are strong for now.
Okay, so but if you have a weak acid and a weak base, then there will be no reaction.
No, they'll react.
Why does it matter if it's strong then?
Why is it better if it's strong?
Why does it matter if it's
Oh.
strong if there's always going to be a reaction?
Oh, the reason that matters is we need to write the net ionic equation correctly. We're just learning how to write the chemical equation for a reaction right now. Don't worry about weak bases. Just put them out of your mind. And when we do chapter 14 on acids and bases, then I'll teach you all about weak bases. The reason that we don't worry about weak bases right now is that weak bases don't have hydroxide in them. There are things like ammonia, NH3. NH3, when you put it into water, it produces hydroxide ions. How does NH3 produce hydroxide? Well, I'll tell you when we get to chapter 14. Yes?
Maybe a dumb question, but why does it matter if it's a strong acid or a strong... Why does
Or
it
a weak acid?
Yeah.
Yeah, because if it's a strong acid, then this would be hydrogen ions and iodide ions.
Okay, so it just matters for the non-ionic,
Yeah.
but it reacts the same way as like ocean.
Yes, they do.
Okay.
They react the same way. I should have said that before. Yep. Because tomorrow and Friday, when you do the lab, you're going to have a weak acid that you'll be reacting. That weak acid behaves the same way as a strong acid would. It will be neutralized by the base that you use, just like if it was a strong acid. Yes?
Does it
Amber?
matter whether the base is strong?
No, they'll react the same. Okay, now I got a couple of examples for you to do. And about 10 minutes left in the hour. Let's go ahead and try this one, just to get us started with the acid-base stoichiometry. I'm going to give you a couple minutes. When you see the word stoichiometry, you sense that there's stoichiometry, you have to write a chemical equation. You can't do stoichiometry without a chemical equation because you need to know the mole ratio between things. So the first thing you're going to do is read the question, and then you're going to start writing a chemical equation, and then see if